Hello and welcome to the session on robot joints and degree of freedom. After completing this topic, you will be able to explain robot joints and compute degree of freedom. We will look at the robot in two ways. That is, one is a serial robot and another is a parallel robot. In case of serial robot, as you can see here, uh, the links are connected in series and the last link is open-ended. So it is not connected to any other element. So this is a serial robot. Whereas in parallel robot, the links are connected in a way that a platform or a show is connected to all the links and all the links are actually parallel to each other. Now if you look at the joints in the robot, there are various types of joints. First is the revolute joint, which is very common joint as can be seen over here. This is a revolute joint as you can see here. This is also a revolute joint. This one is also a revolute joint. This is also a revolute joint. So revolute joint is very common joint observed in the robot. So if you look at the revolute joint, it has 1 degree of freedom. How we define the degree of freedom? It is number of independent motion offered through the joints. Now we are looking at the joint, we also call it as connectivity. For example, a link here which is sliding over the joint, sliding over the axis here. This is the axis and this is a link. This link is moving over the axis and in a way this offset we will call it as from some reference. This is variable. Sorry, this is fixed. Now, when we provide this as a fixed, then this won't move in this direction. This link will not move in this direction. It will only rotate about the same location. Now, if you look at, if I connect it to any other element here, this element can be seen to tracing some angle that is theta. This theta is a variable angle. So, this is a revolute joint. Second one is a prismatic joint. Now, prismatic joint compared to the rotary joint, or we call it as the rotary joint earlier, there this one is a variable and this one moves up and down. So this way it forms a variable moment from the given position earlier. This is a prismatic joint. This is like a latch. We can open and close the door with a rectangular latch. Third one is a cylindrical joint. Cylindrical joint, as can be seen here, it has 2 degrees of freedom. One is it can move up and down, also it can rotate. So this is a case when a latch with a cylindrical rod. So it can rotate and it also can translate. So in that case, there are two variables which define the motion of this link. One variable is this offset from the given position, so it moves up and down, whereas there will be a rotation possible. So these are the two independent variables which defines the motion of the link. One more very common example which provides 2 degree of freedom is a hook joint. Hook joint is especially used when the input axis and output axis they are not collinear. So like a case of a tractor or a case of a agricultural equipment where you need to have the axis at some inclination, we can provide a hook joint. Hook joint also has 2 degrees of freedom. Very common joint used in a robot is a ball and socket joint or a spherical joint. As you can see here, this is a link which is pivoted into a conical, half conical, the cylindrical part. So in that case, this stylus, as you can see here, it can have three independent motion. Which are the three independent motion? One is the rotation about the z-axis. Okay. Second is rotation about the x-axis, and third one is rotation about y-axis. So these are the three independent motion offered by the socket joint. Now, when we want to represent this joint earlier, which I have discussed with you, by joint, for example, revolute joint can be represented by two links connected by a circle, or it can be also represented by a rectangle and providing a variable theta. Prismatic joint by a dashpot arrangement like this, or it can be represented by a rectangle with a cross with provided with the translation possible. Cylindrical joint represented by a pipe-like arrangement with providing 2 degrees of freedom. One is a translation, another is a rotation. Spherical joint, as you can see here, this is represented by a symbol like arrow, or it is an enclosure, right? So this is an enclosure, and this is a rod here, and this is connected. So this stylus, like it can rotate about three different axes. Hook joint is a very common joint for applications in where the axes are not in collinear; they are inclined. And twisting joint. So this joint is also commonly used in robotic system, as I have discussed with you in a previous session, that twisting joint, a very common joint in human being also, like you can see here, I can twist it around the axis. So this is represented by a symbol like this. So two inverted triangles with a variable theta. So twisting joint is also having only one DOF. Now coming to finding out the degree of freedom. So let us define what the degree of freedom stands. Degree of freedom is the minimum number of independent parameters, variables, or coordinates needed to define the motion. For example, if you are defining a robot in a two dimensions or a planar robot, it will have 2 degrees of freedom. And in a space, like we have 3 degree of freedom. A rigid body in a 3D space will have 6 degrees of freedom. What are these 6 degrees of freedom? For example, if I represent the x, y, z axis here, okay, so this is, let us say my x, this is y, and this is z. So there can be translation in either of the axis or rotation in either of the axis. So if you look at, so three translation and three rotation, so there are total 6 degrees of freedom. A special manipulator will have 6 degrees of freedom, or a planar manipulator will have 3 degrees of freedom. Like the very common robotic application or mechanism you might have used in your first year of engineering, that is your drafter. So drafter is a planar manipulator, and if you loosen the knob, so that knob provide rotation about a z-axis, and the linkage will provide a translation in x and translation in y. So that was a planar manipulator. Redundant manipulator is a term when either a special manipulator or a planar manipulator is having more than the degrees of freedom. For example, like in planar manipulator, if you have more than 3 degrees of freedom, or a special manipulator having more than 6 degrees of freedom. So both are called redundant manipulator. Sometimes it is necessary to provide a redundant manipulator if you want to reach to a place which is not easily accessed by the common robots. Underactuated when the special or the planar manipulator having the degrees of freedom lesser than what are they are designed for. For example, 6 degrees of freedom in case of spatial manipulator, or 3 degrees of freedom in planar manipulator. Now, when we want to find out the mobility or a degree of freedom of a spatial manipulator, we can find it numerically by using a Grubler's criteria. So Grubler criteria is defined by the number of links, number of joints, and the constraint provided by each of the joint. So let us say we have n number of rigid bodies or rigidly moving links, and there are m joints. Okay, so we will look at that through an example. First is, let us define the connectivity of a ith joint. So let us say it is I equal to 1, 2, 3 up to m. So M we have defined as the joint. So there are M joints with I connectivity. So I can find out number of constraints put by the ith joint. For example, if we have a um, prismatic joint, so prismatic joint has only 1 degree of freedom. So in that case, the number of constraints offered by will be 6 minus 1, that is equal to 5. So number of constraints we have to find out for each of the connections or connectivity or a joint. So like way the total number of constraints we can find out by summing 1 over m 6 minus ci. Ci is the number of what we say connectivity offered or degree of freedom. We can find out the mobility of manipulator by the equation m equal to 6n. Now what is 6 into n? Suppose in a spatial manipulator, each body will have 6 degrees of freedom. So if there are n elements or n links, they will have n into 6 degrees of freedom minus number of constraints. So number of constraints we already found, so that will be equal to the mobility. So that is called a degree of freedom. So mobility is also sometimes called it as the degree of freedom. So they are often used interchangeably. So this is a Grubler criteria. When we apply it to serial manipulator, let us say we will define it for planar manipulator first, and then we'll look at the example. In case of a planar manipulator, the CI, the same equation, but only thing what will change is the number 3. That is for in planar manipulator, you will have 3 motions possible: X, Y, and rotation about X axis or Z axis or Y axis, whichever way you take it. So number of constraints offered will be equal to 3 minus Ci. Total number of constraint will be equal to algebraic summation of 1 over m 3 minus Ci, and mobility of manipulator will be equal to 3n and the relationship. So these are the two ways. I mean, in case of planar manipulator, there will be 3 minus Ci constraints. In case of the spatial manipulator, it will be 6 minus Ci constraints. So let us apply the planar manipulator case to a serial manipulator. A serial manipulator, it can be used to identify or to track or to pick and place. So there can be different ways we can do it. For example, suppose if I use my hand only in one plane, like suppose I'm going and picking it up and going placing it. So this is a serial manipulator, which is a planar manipulator. And it will have, let us say, I represented it by different joints. For example, this one is your revolute joint. This one is also a revolute joint. This is a prismatic joint. You can see here, this is a rotary joint, and this is end effector. So maybe the end effector is used for holding some job here. So how many joints present? One, two, three, four. So there are 4 joints. Now let us look at linkage. How many links are present? Like it can say there's 1, 2, 3, and 4. Right? 1, 2, 3, and 4. How we define a link? For example, you might have a confusion here whether it is 1 or 2. Wherever there is a relative motion, it separates the linkage. For example, this one slides over this link, and this link has a relative motion with this link. So there are 2 independent links, 1, 2. Then this 3. This is connected to this link, 3, and this is 4. So 1, 2, 3, 4. So there are 4 links and 4 joints. Now, number of connectivity, right? For example, how we say connectivity? Connectivity is nothing but a degree of freedom. So this is a degree of freedom. Let us look at that. What is the degree of freedom of a revolute pair? 1. Number of pair of a second revolute pair? 1. Number of DOF of this one is 1. And this is also 1. So there are 1 degree of freedom of each of the joint present here. Now we find out the mobility, that is equal to m equal to 3n summation of 1 over m 3 minus ci. So n is 4 here, 3 into 4, 12 minus 3 minus 1, that is 2, into 4, that is 8. So 12 minus 8 equal to 4. So it is 4 degrees of freedom. It can be very evident also by the number of joints. For example, 1, 2, 3, and 4. When there are 4 joints, or we can say 4 pairs, 4 connectivity, we can say it as a 4 degrees of freedom. Similarly, we can look at an example of spatial manipulator. This is not a serial manipulator, this is a spatial manipulator. In case of a spatial manipulator, let us take an example of a scara, that is selective compliance assembly robot, which looks like this. This is a scara made by KUKA robot, and we can find out number of links here. Now, very clear can be seen from the actual diagram, that is 1, 2, 3, and this fourth link. Similarly, this is the model created. So this is here also we can find out this is 1, this is 2, this is 3, and this is 4. Okay, so we can see that there are 1, 2, 3, and 4. So 4 links and 4 joints, which is similar to earlier example. And this is a rotary joint, so this DOF is 1, so we can is a revolute pair. This is also a revolute pair, this is a prismatic pair, and this is a revolute pair. So this is a revolute pair because it can rotate like this, so we can use for orienting. For example, if I approach my mouse with this, but if it is not exactly arranged, so I can go and pick it properly. So we can apply it to mobility of DOF, that is spatial manipulator. So it is 6, this is 6. So 6 into n, so 6 into 4, 24. And each one has 1 degree of freedom. So the constraint offer will be equal to 6 minus 1, 5, 5 into 4, 20. So 24 minus 20 equal to 4. So this is also having 4 degree of freedom. This is another example of a parallel manipulator, planar manipulator. So in that case, we can see here the number of links, number of joints. So let us find number of links here. So 1, 2, 3, 4, 5, 6. So I just mark like this: 1, 2, 3, 4, 5, 6, and 7. So there are 7 linkage, and each one has 1 degree of freedom. So you can see here, right? So 1 and okay, what is M here? Okay, so that is important. M, number of joints. So 1, 2, 3, right? Say number of joint. Earlier I marked the single line with the links. Now I will mark double cross line with the number of joints. So this is 1, this is 2, this is 3, this is 4, this is 5, 6, 7, 8, and 9. So there are 9 joints, and each joint has only 1 degree of freedom, as you can see here. The revolute pair, and these are 3 are prismatic pair. So we can find the degree of freedom by using 3n, 1 over n, m, 3 minus vi. We can find out that here the degree of freedom is 3. So the degree of freedom of this manipulator is 3. Okay, so this is not similar to our serial manipulator. Like serial manipulator, we can see that the number of joints define the number of degree of freedom. But here, the number of joints are 9. So it is not 9 degree of freedom manipulator. It's a 3 degree of freedom manipulator. So how we understand this? We understand this by the number of coordinates are required to define the motion, or number of coordinates that will define maybe x, y, and z. So if I define any point here, I can locate its position and orientation. So position x, y, and orientation may be rotation about z axis. So the rotation of a plate. So if the plate is inclined about z axis like this, and position by x and y. So this is a parallel manipulator. So this is all about the joints and degree of freedom. So and we will look at the other sessions to follow. Thank you.